Good evening, everyone. I am Supriti Vijay, the General Secretary of RSM, and I would hereby like to extend a warm welcome to our speaker, Fatima Mireshghallah, along with all the attendees for our event on behalf of the Research Society MIT. Cognizance is an initiative that hopes to bring together all people interested in research in various fields. Our organization is confident that this talk will provide value to everyone attending. Before the presentation begins, I would like to define the structure of the talk today. Our speaker will be giving a presentation on the topic, followed by a question and answer session. The chats will be open to discussion for all the attendees throughout the talk. You can interact amongst yourself and can also put up questions that you have here. To make this an interactive session, you can also raise your hand, and we'll give you the permission to unmute yourself and ask your question directly to the speaker. Our team will also be moderating the chats, so we would like to request everyone to keep the contents of the chat related to the topic only. Having said that, I would like our moderator, Aman Priyanchu, the subhead of Artificial Intelligence here at RSM, to introduce our speaker for the day.
Thank you, Supriti. Good evening, ma'am, and everyone present here. I'm Aman, and I'm the moderator for today's talk. I would like to begin by introducing our speaker for today, Fatima. Fatima is a PhD student at the CSE department of the University of California, San Diego. Her research interests are trustworthy machine learning and natural language processing. She's a recipient of the National Center for Women and IT (NCWIT) Collegiate Award in 2020 for her work on privacy preserving inference and a finalist of the Qualcomm Innovation Fellowship in 2021. She has interned twice at Microsoft Research Language and Intelligent Assistance Group, where she works on private training of large language models. She'll be talking about explainable AI and its impact on privacy. Explainable AI is the artificial intelligence in which the results of the solution can be understood by humans. That is an interpretable output. Now I invite Fatima to tell you more about the topic and explain it in detail. The floor is all yours.
Thank you so much. Thanks for the introduction and the very kind words. And I'm really, really happy to be here. So thank you everyone for attending and thanks for putting this together. It's really an honor. So I'll like before I start, you feel free to ask your questions at like any point during the talk. I'll answer them whenever like they're read to me because I won't be seeing the screen. So and also like even if so what I'm going to be talking about right now is like I've tried to keep it high level, but there might be technical details. So if you have questions about the high level, about the technical details, or even like, I don't know, a question like how did you come up with this idea or like what drew you? So even like those questions, feel free to ask them. And yeah, I would really like to, like have a kind of a conversation as we're going to decide. Don't want to like talk for 40 minutes with everyone bored out of their minds and then you can ask questions. So feel free to like interrupt me wherever there were any questions. So with this, I'm going to share my screen. Okay. Just okay. And let me. Okay, great. So you can see my screen, right?
Yep.
Awesome. So I'll start by talking about just so we're going to be talking about explainability and privacy and like their relation and like how can we use explainability and interpretations for privacy. So with this, I want to first talk about importance of privacy and how privacy is like more relevant today than it was before. And like what are some of the privacy issues that we have to worry about and what are the vulnerabilities and why is it so important now? So like right now, many of us are using all these devices in our homes and like in our workplace or when we go to visit the doctor. Some people have like smart home devices like Google Home or the Amazon device. I won't say its names because maybe you have it and I don't want to wake it up right now. But anyway, like we use those devices. Some people have these Roombas that, like clean the room or even like apart from like IoT devices like these and like, smart TVs and smart fridges and all those. There are also smart meters that some people just use to like regulate the usage of power in like their devices. So they want to they basically want to like help budget their electricity usage better. So they like regulate it using this smart meter. So there are many like tiny little devices that we have, not to mention our phones, smartwatch, whatever. There are a lot of devices that we use, and these are constantly collecting information, right? They're collecting information to help us, like to track our steps, or as I mentioned, to like track our usage of power. But on the other hand, once information collected, no matter like by whom it is or for what reason, it becomes a source of vulnerability. Because if that information is leaked for whatever reason, like even if it's accidentally, then that could be a huge breach of privacy. So like one might think that, okay, my smartwatch is like collecting my location, but it's not visible to anyone. What if like someone attacks or hacks their servers because it's all there in one place? That could be a problem. So just to like recap this, their devices, they're collecting information most of the time just to help us. They're sending them to cloud services or like data collectors, um, which we could trust or we might not trust. And what we receive are better services. So like I mentioned, these services could be voice assistants, security cameras, patient history. It could be like access to genetic data in order to help with the diagnosis of diseases. So it could be a lot of things that we actually like need, and we want to have like better models and better idea of how they work. But this comes with this privacy risk. So another example is like, let's say you take a picture and this was I don't know if people do it anymore, but there was this app that people used to like make themselves look old or make themselves like you look like a kid or swap faces or all those things. So this was not like a Snapchat. It was just a weird application that no one knew where it came from, and then like some people said it was like from Russia. I don't know, I think it was like 2 years ago. And what happened is that like a lot of people uploaded their selfies to like get these effects, and you would upload it to a cloud and then download it once the effect was applied. And what happens is that this might be very benign. They're like giving you a service for free. But what happens is that in your image, like apart from just your face, which is also like, I mean, it could be a huge privacy concern, you're also sending background. So if you're like outside, you could give away your location. There was this study that I think there are only 3 monuments. So if there are like 3 famous buildings, or not completely famous, just unique buildings behind you, people can easily find your location, if they find only 3 landmarks that they know of. So you can easily be located. So this is like a risk to the privacy of where you are. It could also like give away other types of information, like your personality, the activities that you do. If you're posting often, it could give away the timeline of your day, when you're out, when you're in. So like if someone wants to do a robbery of your house, or they kind of just want to hurt you for any reason, you're giving them a lot of information. So what is happening is that you want a service done, but you're sending a lot more information that is needed for that service. If you just want a mask or a filter applied to your face, then why not just send that? Why are we sending all this extra metadata and excessive amounts of information? So this was just like the motivation of like what we are trying to protect, which is the data that you send in order to receive a service, or the data that you send to get better user experience from a service. Now, what is the landscape of privacy literature? So this is like really condensed, but I'll just to simplify it. In the like 2000s, in the early 2000s, when machine learning wasn't that prevalent, deep learning wasn't even happening. There was only like, measuring statistics on data. So that was like what was going on with data. The first rigorous privacy methods that we're still using, they came about. So differential privacy that you might have heard of, and also k-anonymity, they came out in 2006 and 2002. So these are like the first rigorous privacy preserving methods. And they basically, k-anonymity like relies on having multiple instances of one data point, to simplify it, so that like you can't find an exact person's data. And differential privacy, again, simply put, it relies on adding noise to protect privacy. And there are a lot of papers on all of these. This is like a very kind of broad field, and there are a lot of people working on it. And then later on, in like the 2010s, when machine learning became more, people started adopting it more, it became more relevant. And after that, with deep learning becoming more relevant in 2016, we had works on privacy for those. And right now, like more recently, starting 2017 and 18, what people are working on is not just the training of deep learning and how to protect the privacy of the data that goes into this model, but also the privacy of the queries that we send to these models, like the issues that I mentioned, like we take a picture and you like send it. So how to protect those, or how to protect the users, and like how to protect like data that let's say like a smart meters or sensors protect. So like later on, people are working on these things. And so the research has been going on for a while, but similar to whatever happens, the regulations, international regulations, they are normally later to come, but the good thing is that they're coming. So like in 2018, Europe kind of they put this GDPR together, which is like a data protection regulation that has some clauses. You can read it. It's you might have even heard of it because it made a lot of noise, and it was kind of the first regulations for privacy, and it gives people certain rights. It's not explicit, so it's still like hard to apply for machine learning, but like one of its regulations is that people have the right to be forgotten. So if you share your data with someone and at some point you decide that no, like I don't want to share this data anymore, they should provide an ability for you to like retract your data. So they should be able to delete it at will whenever you say, and also if it's used in a model, it should also be removed from that model as well. And then like 2 years after that, California said a privacy act. I know there's some privacy acts in Brazil, and you can like look them up. There are a lot of things happening. And just very recently, this year, like in the US, for US Census, which like releases data about like demographics and like how many people like belong to this race in this county, or like these types of statistics about population, they were using differential privacy this year. And Alabama sued the US Census because they're using differential privacy. So this is also like an ongoing lawsuit, which is really interesting. And there was like some privacy experts wrote this manifestation that like why differential privacy is good, and they like sent it to the court. So now it's like there's this kind of science legal thing going on, which is really interesting. There's not much update on it, so I don't know like what really is going on, but it's interesting to just follow. So yeah, just to again like provide a sense into how different privacy mechanisms work. So as I mentioned, differential privacy, or a series of mechanisms, they rely on adding noise. So if you just add random noise, what happens is that in order to get meaningful privacy, you'll have to suffer an unbearable loss in utility. So like this is one landscape. So you have the privacy and utility. Now, if you also care about computational costs in terms of like time and how much compute you have to do in order to like get a certain level of privacy, then you can like add this extra like third dimension. And here we have encryption-based methods. So encryption is not really privacy. Encryption is security. And if I want to tell, like kind of try to give you how they are different, is that with encryption, you have the data. It could be locked in your model, but there is like, it's in this it's like in a safe that you can't open. So it's protecting your data literally as it is. So it's like it's securing the data. That's what encryption does. But what privacy as a whole means, and it's supposed to do, is that like if you have a model, and if this model is supposed to protect your privacy, it should not be able to leak your information. So basically, privacy is about what you're leaking, and like what the model is encoding about your data, and if it's revealing anything private. And security is kind of like putting a lock around this. So it's like it's not much about what your model is learning and what it's going to leak later on. The difference is like really subtle. But anyway, like encryption-based methods are also considered privacy mechanisms, and the problem with them is that they can give you really good privacy, and they can also give you good utility, But they are really, really slow. And when I'm saying it's slow, it's like 10,000 times slower than like normal execution. And like, if you want to just send a like 4 MB image, because of encryption, you end up having to like send 8 GB of data, which is just like not really possible for, the purposes that we use smart devices. So yeah, this is like kind of a high level look into privacy methods. So differential privacy and noise-based ones, they don't have the computation cost. They normally suffer more utility loss, but you can have encryption-based methods. They don't have loss. They have small loss in utility compared to differential privacy, but they are like in terms of computation really intensive. So I can like pause here if there are any questions before moving on to like the next part of the talk.
Um, yeah, there are a couple of questions we had from before regarding this stage. So,
Mm.
Vedant Rishidas asks, with all our information already online, do you think privacy preserving machine learning will add to the leakage accountability by these companies or social media platforms?
So yeah, well, that's a good question. Like when something is like online or leaked, it's there, so you really can't save it. But the least is that people are becoming like with these things happening, it's like a price that you pay for people to become more vigilant. So you see like all these photos leaking from iCloud, and you see like people's personal data exposed. This kind of makes both them look, it's kind of like an education for people, like data, this is dangerous, like you have to be careful what you put online, you shouldn't just overshare. So I think that like what is gone, you probably can't save it at this point, but it is like a good lesson both for companies. Honestly, companies, I really don't know how much they care. But when regulations start, like when it becomes encoded in the law, then the companies have to care. So that's a good thing. Like with all these lawsuits on privacy, it's like really good because now the companies can also be sued, which means now they have to be more careful. So I really think that like this is making both the companies, even not if they don't really care, they at least have to put on the face and try to like make this happen because they can get sued. And also it helps people become more careful of what they're sharing and what they're doing. So yeah, I hope this answers your question.
Another question, Dasrati has raised his hand as well as asked it. Um, would you like to speak, or should I say your question instead of you? I'll ask this question. Can we use blockchain to protect data instead of PPML, privacy preserving machine learning?
Hmm, I'm going to be honest, I really don't know how blockchain exactly works. But my understanding, I could like, let's just say that blockchain is kind of like a form of peer-to-peer and also like encryption based thing. So the problem with all these is that they're more about security. Let me try to like give a better example of what this means. When you're training a model, so the model is learning from your examples, right? It has to see some data to learn. So even if you're training the model while it's encrypted, you can do that. You can send encrypted data, and the model can also be encrypted. The operations that are happening are still happening. So it's still learning the same thing. You're not changing what you're learning from the model. So let's say that the model is trying to like learn grammar or like learn sentences. If within your data you have this sentence, my credit card number is like, and then you give your credit card number. So in order for the model to learn this, it's actually going to memorize your credit card number. And this is not going to be protected by encryption or like any other type of method because the model is actually seeing this data as it is. You are not seeing it, it's encrypted, but the model is seeing this in like in whatever number format it has, and it's going to learn this. So it's going to memorize this. So if someone else queries this model with my credit card number is, they're going to send it encrypted, and the model is going to work like, again, nothing is in the clear, but when they receive the response back and they're going to see it, it's going to like spit out the credit card number. So you can encrypt everything, but the learning is going to be the same, and it's going to like pick up personal information, and it's going to memorize what it would have memorized before. So these methods, they don't meddle with the learning. So the model still learns the same things. It only learns them while there's like this shield that you can't see what's happening inside. I hope this gives an idea of why these won't help. So that's why we need privacy preserving machine learning methods and like differential privacy. Differential privacy like measures how much the model is memorizing, if you want to simplify it, or like what it's learning. And the like all secure computation methods, they just make sure that this is happening securely. So if someone gets access to the gradients, they won't see the data, but the model will see the data. Yeah. So those things I don't think can fix. They can make your data secure while it gets to the model, but if the model is memorizing, it's not going to work. Okay.
Yeah, he asked a continuation question. Is this achieved using Merkle root? I am believing that's a crypto and blockchain
Yeah.
algorithm.
Yeah. Sorry, I don't know what this algorithm is. Yeah. I know that like for machine learning protection, like in terms of the security, the methods they use, they're either secure multi-party computation or homomorphic encryption. But I don't know like I know like garbled circles. I know some of their algorithms, protocols, but I really don't know the details. So sorry. I haven't done crypto. So my knowledge is very sparse on that.
Okay. Another question by GB Raghava Krishna. Is it possible to create neuromorphic AI which acts like a real human in order to keep our data private? And can we use quantum computing for the aforementioned purpose?
Okay, this is a very highly conceptual problem, like solution. So one thing that I want to make clear is that the hype around AI in general, that AI can do this and it can do that, it's very like Twitter or like, kind of media mainstream thing. AI is really not as capable as people are showing it to be. Like, especially one thing that I'm bothered by most is for self-driving cars, because we are really not at any stage close to having completely like autonomous self-driving cars. And like people say it's in 2 years, I don't really think that. And like I don't think any academic will think that, because there are a lot of things wrong with AI still, that could make things go wrong. So we can't really I don't think we're close to like having some AI thing that is like close to being able to like protect data. And also quantum computing is still like, it's a still concept, right? We still don't have them. And I think the best, like the closest prediction of those things actually happening is like 12 or 15 years. So yeah, if assuming we have those things, then yeah, but I don't see this as a viable option, at least for the near or next 10-year type of future. But like that being said, because if you have quantum computing, then all the encryption-based methods actually go out the window. Because with quantum computing, you can break encryption really quickly. So then, like there are some people who are working on post-quantum encryption methods. So that's like a whole other kind of problem and situation. Yeah. I hope this answers your question.
Uh, he asks another continuation question. Can we take n grams of our brains and make an AI of ourselves? I believe that's ECG of the brain waves.
Yeah, this is very like like yeah, I don't know so much about the field that works on trying to like actually mimic the human brain. So I don't really, that's like a very broad AI question. But I can say that at least at this point, no, we haven't been able to do that. But I don't know if like where the field is. Sorry. Yeah, I'm really sorry.
I think
Yeah. Okay,
um, yeah,
let's continue and we can take the yeah.
yep.
Just okay, cool. So I forgot to say this. So the ideal here would be to like push this curve up so that we can get good utility, good privacy, acceptable privacy without having to spend a lot of computation costs. So now I'm going to like talk about one of my papers which is relevant to this. So this paper is kind of like a sequel to a previous paper I had. I'm not going to talk about that one because I'm going to like try to explain this so that that one is covered as well. But if you're interested, you can like read Shredder. But right now I'm going to talk about like a more recent paper, which is basically on finding, as I mentioned, like we're sending a lot of excessive data, we're putting a lot of excessive data online, and it's all not necessary for the purposes that we want to like achieve. Kind of like the image, you don't need the background, or like in other contexts, there's only some parts of the query that you're sending that you need. So this paper focuses on that. How can we like find the features that we need? This is where the explainability and like interpretation comes in, and only send those. So let's get into that. So what is the problem? Let's review the problem. You have a query image. Let's just focus on images right now. And you want to know if this person is smiling. So you have like their entire face and even a bit of their background. And you're asking your model, is this person smiling? And your model gives you a response, yes, no. And you want to do this in batch. Like, let's say you're a startup who wants to figure out what makes people smile. So you need like, you have 10,000 images and you have to like ask this question. Now, one thing is that if people are giving you their data, the threat is either when they're sending it. So yes, they're sending it through encryption, but someone might like break in, or it might not actually be encrypted. So someone could intercept this connection, steal their image. This is one problem. Another is like, why should people trust you, and why are you gathering all this information? So even if I do trust you, maybe someone hacks into your system. Maybe like someone literally physically like walks into the building and, you know, does something. So there are a lot of threats, and we are like right now focusing on any threat that is apparent as soon as your image leaves your device. So as soon that moment when you send it to like whoever it is, you're losing control. So how can we give you some control back? Like, what can we do instead of like sending this entire image and you know, putting it out in the wild? So we said like we're sending this query. We're sending this query. How do we protect it? So what is this model doing? It's using the features in your image to tell you if a person is smiling. So it's like a neural network. It looks at the image and it makes this decision. So what exactly, if we can figure out what this model that is already trained is using to figure out if you're smiling or not, like how is it making this guess? Which pixels is it using? If we can do this, then we can only send those features and not send the rest of the image and give you some control. So yes, you're sharing the features. We have to share some features. We can't really like share nothing and get everything. So it's a compromise. We are now sharing only part of your image, but at least, you know, like you're not oversharing. So now the question becomes, how do I figure out like which pixels is this model using, or like how can I interpret this? So one method that is called occlusion sensitivity, what it does is that it basically covers parts of your image, like it occludes them, and it sends them to the model and sees what decision the model makes. So that's like an interpretability method. So if we cover this person's face and ask the question, the model is going to have a low accuracy. It's going to be like, you know, it's either saying yes or no. It's probably saying no. So here, it doesn't really matter that much whether it's right or wrong. What also matters is how certain it is. So like if it's uncertain about the decision that it's making, it's like 49% smiling, you know, 51% not smiling. So there's like a lot of uncertainty in this decision. Then we can get that, okay, this person, like this feature that the model was using is around here. So this is an important feature. So like whatever is in this square that I'm removing, that's important. But now if I move this square to this person's forehead, then it's not like the accuracy is not going to change. You can actually try this. Like this is a real example from the data set that we used, and we like literally did this. And so when you put this square here, the model can't make a guess, and when you put it on their forehead, it makes the guess. So, but what is wrong with this, like with this occlusion sensitivity method, is that like what size of a square, and like, you know, how many squares do I have to move? This is like very guesswork, right? What if there's another place, and like, okay, am I like going to like select this person's data in square granularities, or like should I go with like a circle, or, you know, like how do I move this around? And also it's very computationally heavy to like brute force your way through all the pixels. And then you also don't capture the interaction of pixels. Like maybe how would you like take two squares off, like, you know, one from here, like one from another part. So this is like this is used. It's like one of the basic interpretability methods, but it really won't help us here with this, like when we want to use it for privacy. It's good for interpretation, but like not really here for privacy. So what we do is we try to make this more principled. So in my gets, I will try to like explain it good, but this is like always something that is hard for me to make it clear. But I'll give it a shot. But ask questions if you have them. So let's say that instead of like those squares, we take each pixel. So we want to find out on pixel level if a pixel is important or not. So it's no longer those large squares. It's exactly a pixel. So each feature is a pixel. Let's assume that this image has 12 pixels. So let's assume that these large these large squares are each 1 pixel. Now, what we do is that we rely on this intuition that instead of like exactly occluding this image, I can add noise to it, right? I can sample noise from a distribution and add it to this image. Now, if the distribution of my noise for like each Gaussian distribution, we have a mu and a standard deviation, right? So let's assume that the mu's are all 0. We don't want to like change the value of the pixel. That's basically the mean of the value of the pixel, but we want to like have different standard deviations. So the intuition is, if I sample noise from a distribution with a high standard deviation, it's like and we're doing this multiple times. So if I sample this from a distribution with like a high standard deviation, and if I add it to this pixel, then what happens? It's kind of like it's occluding it, right? It's kind of like you're covering this pixel. So if I add high standard deviation noise to a pixel and the accuracy of the model doesn't change, then that pixel is not important. But if the standard deviation for a pixel is very low, and like if I increase it, the accuracy changes, then I like keep it low. So because that means that pixel is important. So what's now the problem of like finding the important pixels instead of just moving this box around? It becomes finding this standard deviation noise tensor, and like what standard deviation of noise can each pixel tolerate. So now if I can, like, while my model is frozen, because I want to like probe this given model, while this model is frozen, I only want to learn the standard deviation of noise, and through that make the decision of what pixels are important for this task of smile detection. So what I do is I like create a standard deviation noise tensor, and I create a mu tensor, and at each run of the neural network, what I do is when I'm given an image, I sample from this standard deviation, because I have the I sample from this distribution, and I have it's a standard deviation and mu. So I take a noise sample, I have this like noise tensor now, and I add this to my image. So it's like a simple addition. So the operations that we're doing is sampling and adding. And one trick here is that when you okay, let's actually continue. So, and then you feed this to the network. So the actual images look like this. So this is like one example image from like our method. Actually, the method is called Cloak. Sorry, I didn't mention the name earlier. And what it does, you still see this person's lip, but you can't really see anything else. So yeah, so this is like what when you train the like noise, what you get. So you're only getting the lip area. And so this is what you do: sample noise, add it, give it to the model, and you actually have to learn the standard deviation of the noise. So I don't know how familiar you are with like back propagation, but basically in neural networks, if you have a given loss function, which is basically like a given target that you want to achieve, you can use this algorithm that kind of through derivatives, it helps you optimize and find your parameters. So here, the optimization problem we want to solve is how to add as much noise as possible while keeping the accuracy at an acceptable level. So I'll show you the actual loss function, but with that in mind, with that high level in mind, we want to find the best standard deviation tensor. So we can actually like do back propagation on this, because the only operations we're doing is this addition and sampling of noise. You can't backprop through sampling, like for those of you who are interested, like you can't really backpropagate through sampling of noise. So this sampling is reparameterized. And if you're interested, like you can ask questions from me, like while we're done with this part, or you can read the paper. But you do this like very simple trick of changing the sampling of standard deviation sigma and mean mu to sampling from a normal Gaussian with like a standard deviation of 1 and mu of 0, and then you give it a multiplier. So you change the sampling to like a simple multiplication and addition. Yeah, so this is like you can easily backpropagate, so you don't have to change your like neural networks function, or like you don't have to change anything, and you easily backpropagate and get the standard deviation of the noise. Yeah, so once you're done, whatever pixel has a high standard deviation, that is an important pixel. And whatever pixel has low standard deviation, it's less important. And the loss function is very, yeah, it's like very, I'll just to simplify it, it has two main parts. One part is the privacy term, which basically all it's doing is advocating for having larger standard deviation for each pixel. So like we want the summation of all standard deviations to go up. That's why we have this. And we also have a cross entropy loss, because at the same time, what we want to do is we want to keep the accuracy high. And cross entropy kind of deals with the accuracy of the model. So it's like, this is called like a constrained optimization. So your main goal is to increase the noise, but your constraint, which is like shown with this lambda, your constraint is to keep the accuracy high as well. So this is like, it's, you can look at it as a constraint optimization. You can look at it as a regularization. It has different names, but it's just like two simple terms for the loss function that we're trying to optimize. And I mentioned this lambda. Okay, so let me just like pause in this slide. And if you have any questions or like you need me to explain something again.
Yep.
Yeah.
Rakshit asks, is it possible to use GANs to generate different versions of the particular essential features of an image and train a model on that synthetic data set created? Would that be an alternative for applying local DP as applied in Cloak?
Yeah. Hey, Rakshit. So that is a good question. Like that is something that I had also like thought about, to just you know, like you can like use Cloak to like apply to sensitive training data and then like create again and only like generate those as you mentioned. But the problems would be so like right now these features are good for that particular model. And what we observed during doing this is that when you train like different models, even with different architectures and with like totally different parameters and like different learning rates, they end up learning the same area. So like I did this with like ResNet and also VGG, and I think even with AlexNet or maybe a different size VGG. With all of those, they all captured the same area. But it might just be that, you know, like they look at something else too. So when you do this, you kind of lose accuracy. So if you like do this, you're doing it for one particular model, and it gives you features for that model. So if you do this to like kind of clean up data and then use that to generate, there are like multiple levels of approximation. So I assume that final model would have not that good of a utility. So that might be a problem there. And another problem would be that like this is acceptable for inference because we want to do this to like protect people's queries. And you can't really use differential privacy for that. But for the purpose you're mentioning, you can use differential privacy. So it would be hard to argue that this is better than doing differential privacy. Yeah, so this would be kind of my two-folded answer to that. Yeah.
Um, is yeah, is that answer satisfactory?
Yeah, I would like to know.
Another question by Gauri is, what is the difference between data perturbation and differential privacy, or is there any difference between both of them?
Really, really good question, Gauri. Yeah, this is a very important question. So differentially private methods, they all rely on some type of perturbation. But what differentiates differential privacy and why we are not using differential privacy here is that you apply differential privacy um, to when you want to release some data, or like you want to release a model, and you don't want particular like an individual's person data to be like to stand out, or to be able to kind of discern from the data. So like let's say that you have like two data sets, and you're going to use them for insurance, and Alice is in one data set but she's not in the other. And if we train two models on these two data sets, uh, if this is differentially private, then the outcomes of these two data sets should be the same. Two models should be the same. So that's what differential privacy gives you. It's kind of like if one person is in or outside the data set, you should not be able to say it. But here, so it's usable for training or for inference on data if you want to like infer a statistic, but it's not good for when you have a deployed model and you want to query it, because there it's like just your data. So the meaning of differential privacy, which is supposed to like protect you, and it's supposed to like protect the membership of one person in a data set, doesn't really mean anything here. So so basically, just to like give you a more concise answer, yes, perturbing data is like differential privacy use data perturbations, but any perturbation of data is not differential privacy. And the reason that like we're not doing differential privacy here is because we have like one person's data that we want to protect. So in general, for like running inference and for querying, differential privacy's definitions don't match the problem, because you're not like giving a statistic on an entire like data set or a group of people. You have one person's data that you're sending. Yeah, I hope this answers the question.
Yeah. Yep. I think that. Yep. So, um, would you like to? There's one more question, but I think we can continue with the presentation, as it can be. It will be related to language and images. So they ask, can you create a distribution tensor similar to the one that you created for any type of data set besides images? So I think they're discussing other data types.
Yeah, let's actually like take it here to not discriminate, because one question no man leaves behind. Okay, so good question. Technically you can, but but I don't think it will really work there, because the thing is like with images, like images are really good, you know, like I didn't know this until I started working on natural language. Like images is very clean. Normally every feature is where it should be. You have a lot of data sets, they're normally all cropped and nice. And in for pixels, like images are really robust. You like perturb a pixel, nothing really happens. Like, you know, you don't even get to understand that it's been perturbed. So it's like really easy to play around and do these things. But when you go to like other, this would work with tabular data or any form of continuous data. But when you go on to language, which is discrete, then it's like a whole different thing. And also like with language, sometimes you put the verb in the beginning, sometimes you put it at the end. So you really can't tell like what is where. It's not stable. So A, it might be harder for the model to like figure out where what is. And B, you can't really perturb so easily, because with words you have embeddings. So in order to like tell the model a word, it has a vector of numbers, and perturbing that vector, they like people have tried to make vectors so that when you perturb them, you go to like a synonym like word or a nearby word, but you might also not. So you might say Alice said hi, and if you perturb the hi, it's not going to become hello. It might become Alice said shoe, you know. So that it's like you can't really do all these nice things there. I mean, theoretically you can, but I don't think it will work with the data, with the type of embeddings we have. It will become more clear, as Aman said, when we like talk about languages more. Okay, cool. So this was the last function. And now here what I want to talk about is that we said that we find the pixels. Okay, good. So I found like these pixels are not important. How do I suppress them? Like how do we remove them? Because we cannot just send some pixels. Like the person who's giving you a service, they expect this certain image. So what do I do? One way is to just like replace everything with like 0 pixels or like with black pixels or with white pixels. So if you do that, the kind of the accuracy suppression, trade-off suppression, let's call suppression privacy. It's like how much of the image I'm suppressing. The trade-off looks like this. So as you see, like as I try to suppress more, the accuracy suddenly drops. And the reason is that, what we hypothesize the reason is that the model is not used to seeing like all black images. The model has a perception of what an image is supposed to look like. And when you like make it all white or all black pixels, it doesn't expect that. So it really can't make a decision anymore. So this is like not the ideal suppression mechanism. The next thing that comes to mind is that, okay, we were adding noise, let's add noise right now too. So you can, just sample from the same distributions with the given suppression ratios, and, you also get good accuracy. So one problem with that would be that because we're sampling from a given distribution and you saw that the mean of that distribution is 0, and also like it's a distribution, so it's like a stochastic when we're sampling from it. And what happens is that for some images, we might not get noise on all the pixels. So it's kind of like you can't be sure that that pixel is not visible. That is one thing. And another thing is that we also like tried something else. We were thinking that let's remove those values, like for those pixels, let's just for now replace them with 0, but then continue training. This time we freeze the standard deviation and we only train the mu, or like the value of the pixel. So it's basically saying let's start with like 0 pixels and then see what the model expects to get. So let's train these suppression values as well. And that kind of gave us the best accuracy. And it also gives you like, you're also sure that that pixel is removed because you're going to use these trained suppressed values for all the images. So no matter who comes, it's going to be the same thing. So it's not going to leak any information through the suppression. So that's kind of how we suppressed. We learned what values to suppress with. Okay, so let's actually see some qualitative results. This was the input image. We ran 3 tasks: smile detection, hair color detection, glasses detection, and smile detection. So for hair color, we wanted to see if the person's hair was like blonde or was it like brunette black. And for glasses, we wanted to see if the person is wearing glasses or not. And for smile, if the person is smiling or not. And for each of these, we have 2 levels of like privacy or suppression. So in the first level, you are suppressing fewer pixels, you're keeping more pixels, and you're getting better accuracy. So like for hair, you're seeing the top of the head. For glasses, it's like around the eye area. And for smile, it's like where you'd expect it to be. So it like one side observation is that it's really cool how the model is exactly basing its decisions on what we would also base our decisions. And another thing is that like even with this first row, you basically get the same accuracy you would. So you have like around 0% accuracy loss. This shows that there's a lot of redundant information in the data that we send. Like you can like get rid of it, even not from a privacy perspective, from a compression perspective. You can just get rid of all of that and just like send a few pixels. Now, if you want to suppress some more, and you kind of remember that there was this lambda knob in the loss function, if you kind of tell that knob to be like, okay, I don't care about privacy that more, let's go easy. Sorry, I don't care about accuracy that more. Let's go easy on that and let's increase the suppression. So you add more noise. Then you end up with fewer pixels. And here, like you lose around like maybe 10% accuracy. So it's kind of like, it's really easy to like suppress 80% of the image without losing any accuracy. But from that point, with like every more percent that you're suppressing, you start losing more accuracy. So it's kind of like, it takes off at that point. And on the bottom, what you see is the actual cloaked image. So if you take this image and you apply cloak to it for each of these tasks, this is what you see. So for the hair, you're seeing the person's top of their head. For their eyes, you actually see their eyes. And for their lips, for the smile, you're seeing the lips. So yeah, if you apply this like method, this is the kind of image that you're going to get. Okay. So now we'll move to some more more technical experiments. So here what we did was we tried to, because this is like all nice, but it's not really like enough to show that this is preserving privacy. It shows interpretability, but it doesn't show privacy. So for the privacy, what we do is we say that, okay, let's assume that the thing we said at the beginning is happening. Someone is gaining access to these cloaked images, and now they want to infer stuff. So what this graph tells you is on the y-axis is the accuracy of the target task. So here the target task is like similar to their hair color detection and eyeglasses detection. And I'm so sorry. The target task is only smile detection. And we want to try to infer other information, like the person's hair color and whether they're wearing glasses or not. So let's say that the images are like this. They're cloaked for smile detection. Now we want to say, we want to see if an attacker can guess if the person is like wearing glasses or what their hair color is. And we see that like there's again a trade-off. So you need to like, and this shows the standard deviation of the like amount of noise. So you need to add like relatively a lot of noise. And at this point here and like here, you see that the accuracy of the attack, so this can be the accuracy of the attack, it drops around 50%. It drops to around 50%. And we should remember that we don't want 0 here, we actually want 50%, because randomness, and since we have 2 classes and we want the decision to be random, so anything below 50% is like, yeah, it's like useless, or anything even at 50% is useless. So you can see that like with losing around, what is this, like 5% accuracy. So this was the beginning, like this is the top accuracy we had for smile detection, like around 91 something. And when you lose like around 4 or 5%, you actually get random results on the attack. So the attack becomes random. So if you suppress like most of the image, I think 95.6% suppression, then you get completely random decisions from the attacker. So this is like a weaker attacker. This attacker only has, it can like only send queries. It's not training a model. We kind of mounted another stronger attack where the attacker can send infinite queries. So in this setup, they can like send an entire data set to Cloak, get the cloaked versions, and then try to train a model with these cloaked versions. So they have all the images they want, and they can actually train a model to decode Cloak, you can call it. Here they are doing better, and we need to like lose more of the accuracy of the main model to like get them to, like get close to 55% or something. But this is like not that realistic, because no kind of querying, no ML as a service will like allow you to make infinite queries, at least not in a short amount of time. So this is not really realistic. Like this is kind of the more realistic type of attack that can happen. But either way, you have an acceptable level of protection. So one other thing we measured here was fairness of the classifier, because now that we're removing like excessive features, we might also be removing whatever features are biasing the model. I'm not really going to get into this a lot, but basically what you need to like, what I want you to know of what we found was that yes, removing the excessive features also makes the classifier less biased, and we measure this bias based on gender. So now it's like less biased towards gender when classifying hair color accuracy. And we chose hair color because that was something we thought that like in the data set it was more gendered, like more blonde people were women, and less were men. So we kind of wanted to choose something that is already biased based on gender. And we showed that like when you actually remove the excessive features, you kind of don't see this bias as much. To summarize this paper, you're using interpretability to get privacy, and as a bonus, you're also getting good fairness. But one problem, if you've noticed, is that these obfuscations are all static, and the features we're finding are also static. I can take questions now, but the next paper that like I'm going to talk about is kind of tries to address this staticness. So if there are any questions so far, maybe we can take them now, and then I'll quickly go over that paper, and we can have more time for Q&A.
Um, I guess there's nothing, there's no additional questions, so I think we can continue it with the next paper.
Okay, great. So I will just like go over. This is actually a short paper, and it was kind of like we realized that this is the limitation, but we were already done with this paper, so we are like, okay, we have to like now write a short paper to address this limitation. So what is the limitation? Let me actually make it clear. Um, with Cloak, when you're like extracting important features for a model, like for smile detection, whatever. Let me go back just to okay. Whatever mask we find, like these masks, these will be used for all images. So if you have something like with people smiling, it's okay, like it's normally the same place. But if the image gets rotated, or if like the person's head is tilted, or for any reason, if you have something that is moving around the image, then this can't be used. Like you can't use Cloak as it is to address this. So yes, so to address this problem, we have like a rather more recent paper that we try to make this kind of detection or like interpretation of what the model is doing more dynamic. So if the object that we're looking for is moving around, how can we find it? So I'm going to start with, and we're targeting medical data sets here because this is mostly prevalent in these cases. And the reason is that like for a task like pancreas detection or pancreas segmentation, the task is to like in this image, try to find the pancreas. And this is a CT scan. And like if you've seen medical data, like CT scans can be very different. Like they can have different like cuts of the body, like they can have different angles. So your different organs will be like at totally different times in different CT different places in different CT scans. And another thing is that we're doing pancreas detection, which apparently like I don't know, but pancreas is like really hard to find because its shape is like it doesn't have a very like kidney has a bean shape, but pancreas's shape like I don't know, it's like kind of it gets squished over by other organs, so it doesn't have like a shape of its own. So normally like what people like even doctors apparently do, this is like what I've heard, is that they find the kidneys, which like here these are the kidneys, and I think this is the pancreas. So like pancreas is supposed to be close to kidneys, but it's like in general very hard to find pancreas. So here the task is a bit different from Cloak. We're not any longer doing this for privacy. We want to use Cloak basically. We want to make it dynamic so that we can use it for when like organs or parts of the image move. And the reason we want to use it is to interpret segmentation and classification models for medical images. So let's say that we have a segmentation model that is doing pancreas segmentation. I want to know how it's doing it, like which organs it's using. So we can use Cloak to actually find out how the pancreas segmentation is making its decision. And the way we do this is that here, instead of like having this one tensor, this like one standard deviation tensor that we had, and we were directly learning it, here we are learning this small model that we call the interpretability model, and the output of this model is going to be the noise mask. So this way it becomes dynamic and it depends on the image. So you feed your image to this interpretability model, and the interpretability model gives you the standard deviation of the pixels. So this is kind of the only tweak you need to do. So this way, like the noise mask now depends on each image. So if the image is different, you're going to get a different noise mask. So we feed it to the interpretability model, and then now we like multiply. This is the multiplication trick that I mentioned by like a by noise with a standard deviation of 1 and mean of 0. We add it just like we did with Cloak. We get the noisy image. Now we feed this image to the main model, who is like supposed to give us a good utility, and this is the model that we want to interpret. And we do like there's this feedback loop. So we do all the training. So here we're not training this, we're training this entire model. And so one question here could be that why are we still using noise, right? Why not just get the mask? If you're getting a mask, just use this mask to get the pixels that are important. And we actually tried this. And the funny thing was that if you don't use the noise, your model won't train. It won't learn the mask. So the noise actually has a smoothing kind of factor because it's like, it's not static. It's not like yes, no. It gives you this kind of a spectrum of values for like if a pixel is in or out. So the noise actually really, really helps us get the model converging and getting the good mask. So we do need to add this random noise. Yeah. And this is it. So like it's very simple. The only difference is that you have an interpretability model. And what was hard for us was like basically coming up with a good architecture for the interpretability model and how to train it so that it can actually like give us information. And we also wanted it to be small, right? We don't want it to be the same size as the actual model, because then like who's going to interpret that? So this is kind of like a nice GIF of how the method works. So these like pixels are like the more we are adding noise, and so the red parts are the pancreas. You can see that they're like very different in different images. And what you see, like how this helps, is that you can see like here, this organ is like one of the last organs to get noisied. This means that this is like what is most important for this pancreas to be detected. So the last organ that goes before the pancreas is this, which is the kidney. So it kind of shows that like this model is depending on the kidney to make a pancreas segmentation kind of decision here. Or like here also, this and this, like they are also like among the last to go. So yeah, so you can see like how the model is finding the pancreas, and also the pancreas itself is the last one to get noisy. So yeah, so this is kind of this paper is like, there are some details, but it's mostly like engineering and like feature tuning and how we got this to actually work with such dynamic setup. But there isn't any kind of like more innovation in terms of like the method that we use. So if there are, okay, at this point we can like we can stop and just do Q&A, because like I'm done with all the interpretability stuff. But if people are interested in like some natural language processing kind of high level overviews, I can also continue with that. So whatever you think the feel of if people are tired of me talking all the time, we can just do a more interactive, yeah. So whatever you guys think.
Yeah, so I think there are no questions in chat. However, we have some old questions submitted to us by a form. One of them, which is related to this topic, would directly be can this noise methodology for interpretability respect privacy as well? Whereas can it respect privacy in the sense that can it be used for privacy as well? This is asked by Harsh Rathod.
Okay, so this is a good question. I can have two interpretations of it. So one interpretation is like, can we use this kind of interpretation for privacy as well? And the answer is like, yes, like we used it in Cloak, and here for this paper, you can also do it. The reason we didn't do it is that like for medical use cases, you need better guarantees. So I didn't really want to like be like telling people that you can use this for privacy of images in medical domains, because it's not, there are no guarantees. So I wouldn't recommend doing that. That's why we didn't do it. But another answer is if you want to look, if I want to like take your question another way, it could also be that, does this way of interpreting models respect people's privacy? Which then the answer is it's not that clear. It could be no, because whoever's data I'm using to train all this interpretability stuff, their data is like, it's leaking. So for them, like, yeah, so it has to be public. So whatever data you use to kind of get how the model is making its decision, you should either not care about its privacy, or it should be public, or you should use differential privacy when you're training these noise metrics, which I don't know, if you do use it, you're still going to get a good interpretation. But yeah, so that's the second answer.
Yeah, I think there are audience which want to continue with NLP implementation with interpretability and privacy. So we can continue.
Okay, great. So I'll go to the NLP part. Um, so this is like a paper that we had, but I don't want to really get into the details of the paper. I want to just give you an overall high overview. I'll tell you about the paper, but I don't really want that to be the focus. So with this, I'm going to like start talking about the threats in like natural language processing, and basically like the privacy threat. So I don't know if you've seen this. There's this famous paper that came out like in February. It was called Large Language Models Are Stochastical Parrots. And what that paper was basically saying, it was studying like what happens when you have this large language model that is trained on people's data. So what is a language model? A language model is actually, it's not by definition neural. You can have like table-based language models or like n-gram-based ones, or you can. There are many different types of them, but right now the most common ones are the ones that use neural networks, and their goal is to model the language. So what this means is that they're unsupervised models. You give them like large corpuses of data, and they're supposed to learn the sentence structures. So the way they learn it is that you just feed them and you kind of train them to guess the next word. So you like tell them hello, how, it's going to like say are you. So the most common one that all of us have used is like when you're sending emails in Gmail, and I think other service providers have this now. You type half of the sentence and it predicts the next. So that is directly a language model that is doing this. So the job of a language model is to like see part of the sentence and guess the rest of it, or guess the next word. And that's how it's trained. So because of the fact that it's actually generating language itself, it could be a huge privacy risk, right? And it also could be a huge ethical risk, because, like, what if it said something impolite? What if it said something racist? What if it leaked someone's credit card number? All these things could go wrong. And I think like you might have seen that how language models or translation models, they say racist or sexist stuff. Like when you say this person is a nurse, then it becomes she is a nurse. Or like if it's a doctor, then it's he is a doctor. So there are all these things that happen with language models, and in general with like NLP models. And the reason that they are more prevalent here is that like with vision, I don't want to like compare with vision, but like with tasks other than generation, because this is also, I think that there was problems that like GANs only generate white people images. Like if you give them black people's images, they don't look good. So it's also there. But here it's that these like language generation models are actually, it's kind of different than an image, because image you have this like actually image generation. I don't know how much it's used, or at least we don't use it in our everyday lives, but we use language models way more than like we like to think. Our keyboards, when we're typing, it's a language model. So I think it's more kind of, it's something that people see more. So maybe that's why it's like, I don't know. I feel like this is a bigger problem right now, to like fix these things, and also to tell people that these problems exist. It's not like this magic box that you feed all this data and everything is good. They actually learn whatever you tell them. So if you feed them like, racist data or sexist data, that's what they're going to say. If you're like impolite, that's why the parrot, it's like it's learning what you feed it. And okay, so let me actually like wrap this part up. And this is why like we want to focus on the privacy concern right now. It's that it can leak your information. So if you train it with private data, it can leak information. And there was do I have okay, yeah, there was actually this recent attack, which is like now kind of famous, was that I don't know if you know OpenAI's GPT-2, but it's like a very common language model that people use. And what happened was that a group of researchers, they were able to actually extract someone's phone number, email address, you can see like the corporation name, and even their physical address from this model. So it was memorized in this model, and it's like some real person's information. And they actually checked with OpenAI, and this was like really this person's address. So even like, because right now the argument is that, oh, this is all public data, it's all scraped from the web, so it doesn't matter. But this shows that it actually does, right? You can't control, like, I think this really goes well to the question that was asked at the beginning, like once something is online, it's no longer private. So yeah, what happens in these cases? This kind of really showed that there is a problem with like leakage and memorization of data in these large models. And just to like give you an idea, like these language models, they can have anywhere from like 100 million, 170 million parameters to, I think, like, I don't know how big, I think there are even billion parameter large language models. So it has like a lot of capacity in terms of the parameters that it has to memorize. Yeah. Okay. So yeah, another example, like my credit card number is, and you can like extract someone's credit card number. Now, with sorry, with not just language models, if you want to like look have a general look into like the threats with language and natural language processing in ML and NLP. So you have language models, they generate data, that's like one problem. But there are also other threats. Text generation is only like very important because it's like literally giving you the text, but also with like classification or from embeddings. Embeddings are basically vectors for each word. So in order to like get the model, because the model has to look at digits and numbers, right? So for each word you map it to a vector. That's the simplest way to explain an embedding. And you feed these embeddings to the model. So even the embeddings of a word can leak information. So there are also attacks on that. So basically, like any part that has parameters and is learned on data, it can leak information. So in this setup, like where the leakages are and the ones that we want to focus on is when you deploy this model, like either on cloud or on a device where like people are querying it and using it. So just to make sure that like we have the problem and the goal, we're assuming there's a language model. People are going to be using it to like either use it for their keyboards or send emails, and it's supposed to complete their sentences. And we don't want that language model to leak information. So with this in mind, how do we do this? Let me just. So the way we do this is the way that like our approach basically does this is we say that if you have a string and you want to train your model, so now we're not looking at that deployed, the setup that I was talking about in Cloak. Here we are literally going to train the model, and we don't want this model that we're training to learn people's information and spit it out later. So so how do we do this? Like we say that if a string can be used to identify who wrote it, then if we leak this, we can define this as a privacy breach. So if my sentence says that like I'm going shopping with Susie on Tuesday, and this makes it like people know that like they know Susie, and then they will know who I am, so they will be able to like know who wrote this sentence. Then if I leak this, if I learn this exact sentence, I have a privacy breach. So now I have to change this sentence or the way that the model sees this sentence in order to kind of prevent this leakage. So high level, what I want to do is like, ideally, I want this sentence to be learned. I don't want to like lose these sentences because it has good structure. But instead of like learning it as I'm going like, I don't know, shopping with Susie on Tuesday, it can be memorized as I'm going shopping with like a more common name, like with, I don't know, with Alice, or I'm just going shopping and on Tuesday can be like on the weekend. So I want it to be changed so that it can't be linked back to me anymore. And so this kind of, this gives you a level of privacy on the authorship. So you're protecting the author. You can have this on different attributes. Like maybe you want to protect people's political views. So then you can kind of use this linkage, but to political attributes. So I'm preventing linkage to authorship. You can prevent linkage to age, to any other feature that you want to protect. So this kind of gives you a knob to play with. And I'm really not, I don't want to get into like the details of this, but it's very similar to the methods you saw before. You have a utility term, a privacy term, and the only difference here is that we have a discriminator. So the person who's telling me if I'm leaking information or not is this discriminator. The discriminator tries to get my sentences from the language model and guess who wrote them. So, and if it can guess, then it kind of sends a feedback to the language model, and it's like, fix it, you're leaking information, kind of like that. Let's not, and these are like some of the experiments. It's not that important here. What's like one attack that could occur like this is, as I mentioned, it's called a tab attack. You say, I will meet, and you want to extract information. So it becomes like Alice at the dogs. So if I can extract this sentence from the model, then I have a problem. So this is like one type of attack that we mounted to show that our method works. So it's like, you press tabs and you get the output. So this was like about this work, but now going back to the embeddings thing that I mentioned, that like embeddings can also leak information. How those attacks work is that you have a sentence. So the sentence is like, this is a training sentence, like X a star. You have a model that is supposed to give you an embedding. You feed this sentence to this model and it gives you an embedding. So I don't know if you've like heard of BERT. BERT is like its sole purpose is to give you embeddings and to give you like good embeddings for your sentences. So embeddings are like really, really important in NLP because that is like kind of the pixel value that you have in computer vision. So it's like what the model sees. So there's like this whole field on getting better embeddings. And then you can use these embeddings for any downstream task. It could be for like generation, question answering, text classification. So then you have another like classifier or a model that uses these embeddings. Now, there are actually attacks that are using this embedding. So only a vector, it's not even a sentence. So maybe you have like a very long sentence, it becomes condensed into this like 700 element vector. And just by seeing this vector, people can either do embedding inversion, which means they can invert this embedding into your actual sentence. And so from the numbers, they can go back to the sentences, or they can do attribute inference, which means that they can't get your entire sentence, but they can guess like one name that is in it or one attribute of this sentence. And also, there's another type of attack here that's called membership inference. So here they can't guess what your original sentence was, but they can guess if your data or if this sentence, whatever it was used in the training of the model. And the problem with like membership inference is that if you have models that you have a medical model, if you know someone's data was used in it, you can guess that this person had the disease. So if it's like on diabetes, and if you find out that someone's data was used, then you know that they have diabetes. So that's why membership is important. In order to mitigate this, there is this thing called like private embeddings. It honestly, like, people don't use it. So it's like a nice academic work, but they don't use it because this doesn't really solve the problem. But how it works is that it tries to perturb embeddings, as I mentioned, like with adding noise to the values. But the difference is that it really tries hard so that it doesn't map the words into unrelated words. So the example that I made, that like if you say like hi, it tries to map it to hello and not to shoe. So some examples that they show is that like for encryption, if you have public key, it's like, and if you like you kind of want to change it, you have these like levels of what it changes them to. It like changes it to ciphertext or into encrypt, or or if you have like futsal, it like becomes lacrosse or hockey or all these. So it kind of changes these words. So I'm sorry, the original word is encryption. So if you really want to perturb it a lot, it becomes public key or ciphertext or encrypt, which is like the least private, and so on for these ones. So like a spacecraft becomes Aerojet, Apollo, or like spacewalk. So you have like these levels of granularity that you can perturb with. Yeah. So sorry if like this part was not really that clean. I just kind of wanted to like give an overview in the like most interesting problems that go on with the privacy of natural language processing. And like, I know that the talk was sparse, but really the research is also sparse. Like, people are only working on privacy of language modeling and these embeddings. So they aren't really working on classification yet. There's like a lot of problems that have been addressed to some level in like machine learning and computer vision that have not yet been addressed for NLP. So yeah, so like this is like basically most of the work that is going on in this field. And just to kind of wrap things up, like what we looked at was like an interplay of utility, privacy, and interpretability, and how like one can be used to like make the others better, or like you can use interpretability to get some privacy, but like maybe if you're like using private methods, the model is not still as interpretable. So there's a connection going on with these. And yeah, so, and like some of the future directions that we can really look at is more privacy and interpretability of natural language processing, both in like central setups, in federated learning, and all those. And also just in general, like how can we have fairness? How can we add fairness to this mix? And like, because there's also this saying that you can't have both fairness and privacy. So how does that play out? Yeah. So with this, like, I conclude the talk, and feel free to email me if you have any questions, and I'm also here so we can do Q&A. Thank you so much for listening. I went on for so long.
I think it was great. And with respect to NLP plus privacy, there were some certain examples like GitHub Copilot recently leaked API keys and other
Exactly. Yeah,
examples.
yeah, yeah, yeah. Yeah, that's a
Uh,
very good example. Yeah, yeah, I remember that. And I was telling, I don't know how API keys, how important they are. I was telling my friend that like this is a huge leakage. And what he was saying was that like API keys aren't leakage. I don't know if they are or not. But for me, as a person who works on privacy, like even if like it's something that is written on people's faces, but it's leaking, it's a problem. So it doesn't matter that it's not technically private, it's leaking. You know, it could have been anything else. It could have been
yeah.
someone's comment, you know, and yeah.
Another question continuing that was asked by Ayush. With large models trained on public data like the GitHub Copilot, how can we address concerns of breaking individual users' copyrights, for example, with code?
Oh, so for I think for copyright issues, I don't really know what they trained that model on exactly, but for copyright, like you can't. I think for that there has to be like a precursor level that you know if a code is copyright protected, then you should not just use it. Like you know, that's I think what they should do, because that is like a whole legal issue of itself, and I don't know if you can like have a machine learning mechanism that only learns the not copyrighted parts. And I think that's like more of a trouble than just not use it, because there should be like lots of open source not copyrighted code available that they can use.
Yeah.
So yeah, I think that's they're not using it. Yeah.
Um, Another question which Samir asks, how can privacy preserving machine learning be integrated with other AI subdomains like health and AI or even sustainability?
I'm sorry, can you repeat the first part again? It
Yeah.
broke.
How can privacy preserving machine learning be integrated with other subdomains like health and AI and sustainability?
Hmm. That's a really good question. I think with regards to health, there are already some kind of there's some organizations or some movements that are trying to do this. I know that there's like one in MIT from Ramesh Raskar's group that like they are it's called Path something I forgot. But anyway, like they're actually trying to like get healthcare and like privacy to kind of integrate them and like answer healthcare related privacy concerns. So there are actually right now like some movements and some work on that, which is really nice. And also like Open Mind is working on that. Yeah, so I think that there are other people who are doing this, which is like really nice. And if you're like interested, I can like send the links later on to like these kind of petitions or like these types of things that people are doing. I know there's like a lot of like coding and open source stuff going on, so they might like need help for those or also for the research. Yeah.
Yep, definitely. I think one more question asked by Gauri is, are there any downsides to adding privacy to ML models? And how does that affect interpretability or explainability?
Good question. Okay, so this is like a topic that people don't want to talk about. So the first downside is that if you use differential privacy, which is like the rigorous guarantee and everyone is doing, um, in like especially with deep learning, you see a huge loss in the utility of the model in order for you to get any meaningful privacy guarantees. So that is a problem, and there are like a lot of papers on it. But that's the most obvious one. Like another problem that we have like worked on to we actually like have a paper with Rockshit on this is that using privacy with differential privacy actually like hurts fairness of the model too. So that is also something that people debate, that like is it the privacy part that is like hurting the fairness of the model? And by fairness I mean that when you use differential privacy you lose, I said you lose accuracy, you lose more accuracy for some people and less for some others, so it's not fair. And yeah, so like the question there is that like, is this the privacy that is doing this, or is this just the way that the algorithm works with like DPSGD? So there are some questions there that like, does privacy harm fairness when you use differential privacy or not? So this is another question. And in terms of like interpretability and explainability, there are also some new papers on it. Again, we have a workshop paper. With Rockshit on this. And short answer is when you use differential privacy, the model does become harder to interpret. So there is also an issue. And that is like one side. Another side is that like, do interpretability methods harm privacy? Which like for this one, there's a paper by Reza Shokri. I can like make a list of these and like share them with you, Aman, at the
Yeah.
end, and then you can maybe send it. Let me just write down the papers. Yeah. So yeah, so there is like a lot of there are debates on like the intersect basically how privacy and interpretability and fairness they all interact. Yeah, and like the consensus like with respect to differential privacy is that it could really be hurting fairness to some point. So that is like what people are showing. Yeah.
Um, I guess there are no more questions. So, uh, thank you, Fatima, for that amazing session. Really enjoyed the discussion over the motivation behind privacy as well as the different impacts it has. Um, Now
Thanks.
I will ask Suprati to give the vote of thanks.
I think you're muted.
Suprati, you're muted.
So sorry for that. Now, so thank you, Aman. Now that the session is concluded, I would like to thank our speaker, Fatima, and our moderator, Aman, for such an amazing event. The talk has been very intuitive and has given us a lot of insight into the field of privacy and how we can interpret AI
Thanks.
decisions here. So, from covering the basics of the topic to explaining the research you have conducted in the field, the entire talk was very wholesome. The pictures and the slides were very interesting, and it made us enjoy and understand the topic even more. So, we look forward to having more of these sessions with you in the future. And we would like to even thank our enthusiastic audience for making this event successful. If the attendees have any more questions on the topic, feel free to approach us after the event and we'll connect you with the speaker. So, like I'd mentioned before, the Research Society MIT was formed with the main goal to promote the idea of research among students and connect them with professionals and experts from all around the world and help create a society of like minded individuals passionate about research. We host a range of events, webinars, alumni talks, and paper presentations. So please do follow us on our Instagram and LinkedIn for updates and check out our website for collaborations on ongoing projects that you may be interested in. We have posted the links for the same on the meeting chat. Even if you're not a part of RSM, you may feel free to approach us for resources or any questions related to research or any project ideas you would like to collaborate with students on. We would love to know your feedback or the suggestions that you have. Thank you so much, everyone, and have a pleasant good night.
Thank you. Yeah, thank you so much. Thanks for having me. And also, like, if someone wants to stay, we can like, I can stay for like 15 more minutes if people have questions about like PhD and those types of things. Because yeah, I really wish we had time sooner. I talked so much. Sorry. But if there are questions that I can help with, I'm like glad to stay longer if that's possible. If there isn't like another thing happening after this. So if someone has questions they want to ask about like PhD life or like decisions or I don't know, like not technical stuff even, I'd love to like stay a couple of minutes longer to, talk about those.
That's amazing, Fatima. We actually did have a question about this, but
Sure.
we couldn't cover it because of the time
Ah,
limit. So one of those questions were that how did you come about finding your niche in privacy and NLP? Like for people out there who still haven't found their area of interest, how do they figure that one out?
so this is a really good question. Like when I started PhD, I didn't have a master's degree, so I like really didn't know what I liked that much. And my undergrad was in hardware engineering, so I was like pretty much a computer architecture person by training. I had no idea what machine learning was. I had no idea what AI was. So and then I like started PhD and we wanted to do some stuff regarding like hardwares for AI. So I started learning like AI and ML at that point. And then we were working on like making more efficient neural networks. And I didn't really like that. We were working on quantization to be specific. And I didn't really like that. But, I was working on it. And then like at some point, because with quantization, you also have noise. And so all this, like the whole, like how can this noise be used and all that kind of draw me to privacy. So like I was thinking that like maybe this stuff you're doing with noise, we can use it for privacy. That's how I actually accidentally started doing privacy, and when I like worked a little on it, I realized that I really like it, and I really like the aspect that you have to think about people too. In most like machine learning stuff, people don't really think about people that much, although they should. But here, like with privacy, you really have to consider that, and that's what I really liked about it, and I kind of wanted to stay in the field. So I didn't like go back to the architecture stuff that I was doing. I just kept working on privacy, and then like after a while, like I went to my first internship at Microsoft Research, and there the project was natural language processing. So I kind of learned it, and I was like, oh, this is more relatable to me than the stuff I'm doing, like because I didn't even realize I'm using all this, text every day. So I kind of realized that now I really like this, and so that's like what I'm working on. And one general advice is that something that people are afraid of, especially when they start a PhD, is like they think that they have to like focus on this one thing, and they have to find it quickly, and then just do that. So as someone who's like done a lot of different works in different fields, I and like also my advisor thinks the same, that it's okay to like explore different things, and if you like something else, just start working on that. It's good to have an overall like umbrella, but don't be afraid to like try different things, even if it's like, I don't know, the fourth year of your PhD. You find work on what is interesting to you, on not on like what you have to do. And it's totally okay to have your like feelings change and work on, because whatever I work on, I'm like, oh, this is interesting, like I can work on this. So yeah, don't be afraid, and don't feel like you have to find it quickly, and also like try different things, because from outside things are different than what they are like when you actually do the research. Yeah, I hope that answers the question.
I think that's amazing. Your entire journey of finding and getting to know more about privacy and NLP was just very amazing.
Thanks.
Does anyone in the audience have any questions related to anything in general, PhD, or any non-technical that works too? Um, I don't think we have, but
I
all
think there's a
right,
question.
yes.
Yeah.
Yeah.
Um, so Muskan is asking that what is it like to be a woman in STEM from a PhD perspective? Like,
Mm. That's a good question. And so the honest, like, because I've been in different fields, and like I've been to many different communities and their conferences, like security, I don't know, NLP, machine learning, computer architecture, web. So like in the past 2 years, I've been to like all those conferences, and just like an overall demographic view is that there are very fewer women in like hardware and computer architecture. So when I was working on that field, I did really like feel like there aren't many people, and in the lab I was the only girl, and that is kind of it doesn't I didn't feel left out, to be honest, or I didn't feel like discriminated against. But what I did feel like was that there are some things that other people don't experience, like that like you feel like girls or like underrepresented groups might experience, and you want to talk to people about them, and there's like not many people to talk to. But the good thing with ML is that there is this huge, like there is women in machine learning, there are a lot of small initiatives that are starting, and I think those are really helpful. So like honestly, yeah, you do notice that you are like definitely the minority, and like there aren't many people like you out there. And but I think that it's not maybe as bad as it was 20 years ago. I don't know what it was like, but just talking to other women who were there back then, it's not like as tough as it was. So I don't like, one good thing is that I've only like a few times felt that like I'm being undermined because I'm a woman, or like people I'm talking and like someone starts talking over me. I really hate that. And I've like, whenever people do this, I tell them that like, stop interrupting me. Like, I'm talking, don't talk over me. And yeah. So, but this like has happened maybe like once. It was worse when I was in Iran. So I'm from Iran, and like it had happened to me a lot. Like in class, the professor would ask something, I'll give the answer, and then he would like look at me and then ask it again, and then another guy said the same thing, and it was like, good job. And I was like, dude, I just said it. So this had happened to me in Iran before, like multiple times, but here, like, I haven't seen it. And yeah, so I would like to say that I'm like hopeful, and I would really encourage girls to, like, not be afraid that there are not many women. There are more and more women, especially in larger fields like ML. Yeah, there are lots of girls. So yeah, definitely like do apply, and yeah, don't be afraid. The environment it's nice. Yeah.
I think that was very brave, and you're like an inspiration to a lot of
Thanks.
girls and women out there. We actually have a few more questions. One of them was, does documentation of your work matter in any PhD or anything?
Yes, yes, documentation like matters a lot. So one aspect is that you want others to use your work and to cite you, but you just want them to use your work, even if it's not just for citations. So then documentation is really, really important. You like it's really good to have, especially with your code, how it worked, so that people can use it and they can benefit from it. So that's one thing. When you're submitting papers, also I've seen that reviewers really like it when you have your code and documentation and everything is like nice in tables. So it's also important there. And apart from all these, something that happens is that like you write a paper, you submit it, and then you go work on another project, and then like 4 months later it gets rejected. Now you have to like run some more experiments. If you don't have documentations, you are not going to remember anything from the code, or like it's going to be a nightmare. So what I do, which really works for me, is that there's this application called Notion, and I think it's actually free for students. It's free in general, but it has some capabilities that you have to like pay for. You don't even need those, but if you want those, it's free for students. And it's really good in keeping track of what you're doing and documenting things. So whatever I do, even if it's super stupid, I do write it, because I know that like 2 months from now, when I have to do this again, I'm not going to have any idea. Especially like when you do like 1, 2, 3, 4, like you get to the fifth project, you have no idea what you did for the first. Like you have this very, yeah. So it really helps. And I think it's really important to like start documenting like as soon at any point that you can think of. Just some people use Google Docs. There are a lot of tools out there, but do definitely document stuff for yourself, for like other people who want to use it. And sometimes you like leave a lab and someone else has to like do the rest of this project you were working on, so it also helps them. So yeah, document everything. Nothing, no detail is too stupid or small.
Right. We had another question. Likita is asking if you could like share your experience on joining Microsoft Research, and how difficult was it with the competition out there to get in there and secure
Hmm.
an internship?
So honestly, like what I did, so one thing that does help, I think, is that some people like their advisors have industry friends, like either not just for Microsoft, like in companies, and it's not, you don't get it through friendship. You at least get the interview because they know you. So it's like they recommend you, you get the interview like that. I didn't actually have that because what the field I was working on was different from my advisors. He was doing architecture at the time and I was doing privacy. So I just applied to like 20 positions, I think, in Microsoft. There were 5 interpretability related ones. There are actually a lot of specific positions. And I got an interview from only one of them, which was, I think, like out of sheer luck, honestly. And the luck was basically because of, I think, two things. It's that like 2, 3 years ago, there were even fewer people working on privacy. And the project they had in mind was very connected to the paper I had just published. So I got really lucky that it was like such a good match for me that I got the interview. And then the interview is like mostly with research interviews. Companies right now, this is a really good thing, they don't do coding interviews. So with like MSR, I didn't do a coding interview, and also with Google research internships, you don't do a coding interview. Facebook does coding interview. Amazon, I think, still even for research, they do coding interviews. But Google and Microsoft don't, which makes me really happy because I'm really bad in like coding under pressure, like when someone is watching. So there wasn't a coding interview. There was just research questions that I had to answer. And like they said, they were also talking to other candidates. And I remember that like I was really stressed because, it was like either like I felt like this is like my chance, like how lucky do you get to, get an interview. And And especially for me at that time, because I've switched advisors, by the way, but at that time, because what I was doing was different from my advisor, I didn't have any chance of him being able to get me an internship. So it was kind of, it meant more to me that like this is something that I'm just getting all by myself. And yeah, and then like I think 10 days later, they kind of said that, okay, like we decided to give you an offer. And I was right on the spot. I was like, yes, of course, I accepted. I don't even want to think about it. And yeah, that was that. So like, if my advice would be to just apply as many places as you can. And if you like through LinkedIn or through whatever kind of through conferences, if you can meet researchers themselves, recruiters are not helpful, to be honest. Like talking to recruiters, I never talk to them. They can't really help much. So just talk to researchers, try to find them, try to make connections, and also try to make your work visible. All these really help. And like have a nice portfolio, have a web page, have have like your resume, have everything, and be okay if like you get rejected. I remember like my first, actually even my second year that I got like the MSR thing, I got flat rejected from Google. So I didn't like even get to like, I submitted and like the next day I was rejected. So things are random. Like don't be disappointed. Um, and yeah, so that's kind of my advice is, and also like try to increase your visibility as much as you can. But not being disappointed is the most important thing, because like we all get rejected like all the time. And even like people who you see that they have like awards and stuff, like they've also been rejected many times. So you only see the success, you don't see the rejections and all those things, and keep that in mind.
Right. I actually had another question about your PhD journey. Like, did you start your PhD journey before or alongside masters? And if you did, then how was the experience of navigating both together? Because especially from the planning and organization perspective, like, so this girl who's asking this is working on 2 degrees simultaneously, and she wants to know how great it was. Like, how did you handle everything together?
Hmm. That's a really good question. So I didn't have a master's degree, so I was kind of like I got my master's when I also started the PhD. So like in the second year, at the end of the second year of my PhD, I also got my master's. And it's not, I like, honestly, it's not too difficult, because the only thing is that we do master-based research, which is we do research-based masters, which is like, it's like your same PhD research. So I didn't have any extra like burden for the research part. The only thing was that I had to take so many courses, and it's difficult to do courses and research. So that was a bit hard. So my suggestion is like to get your priorities straight. If you feel like if you are equipped with what you need to do the research, try to take some courses that are easier. Don't take hard courses. But if you need to learn stuff, then do take. So especially in the US, like it's really important to balance this. Like don't take too many hard courses together, and like ask other people, is this course easy? Like was it easy last year? And always like take one of your courses from easy courses that you may already even know, and like try to like spend that extra time on research. But if like for me, one mistake that I made was that I didn't know machine learning, and I didn't take good machine learning courses at the beginning. It's kind of like something, it's like a hard pill you have to swallow. You have to learn what you don't know at the beginning, even if it's hard, but just be done with it. I didn't do that, and that was something that like it took me like a whole year to actually learn the machine learning knowledge that I need. But if I had taken the right courses at the beginning, it would have been better.
Right.
Yeah.
I think we're done with most of the questions, and it was really amazing to hear about your journey and to
Thank you.
actually took out the time to let us ask you these non-technical questions as well, which is really really amazing.
Yeah,
Thank
thank you so much. It was really nice. And I really want to thank the audience for like taking the time. It's night there, it's Saturday. So like really, I really appreciate this. Yeah. And like, feel free to like email me with more questions if you have or whatever. I would really love to help. Yeah.
you. Right. Thank you so much,
Thank you.
Fatima,
Thanks so
and
Thank
much.
you.
Thank you.
we
Thanks.
really liked having you over here.
Yeah, I really enjoyed this too. Thank you. Thanks. Have a great rest of the night and weekend. Thanks.
Thank you.
Thank you.
Thanks. Bye bye.